All right. So this is page number 5, kind of the next topic of this. This is the third right-hand rule, and this is the topic of force on a wire that has current in it when you place that wire into a magnetic field, a separate magnetic field. Don't get this confused with field around a wire created by that wire and current. This is a current carrying wire placed into a separate magnetic field, and this is where those magnetic fields are interacting via a force. So this last piece is the actual force on this, and this is at the heart of an electric motor. This is where you take electricity, run it through something to create a magnetic field, and let another magnet push it. And so let's get going. Magnetic force on a current carrying wire shown to right is directed which way? So which way is that force? Again, you got your right hand. If you're doing it with just your palm, right? We didn't do this. You just place it out and think palm is the force because you slap somebody with it. That's a forceful thing. So the palm is the force. Thumb is the current, just like the first right-hand rule. And then your fingers are the field because you've got multiple of them. That's a way to do it. But again, if you like to use the 3 fingers as well, like I do, then you can make the little L for your current and field, and then stick up your middle finger to get the force. Either way, I'm going to take my thumb and I'm going to put it up on the page. I'm then going to turn my hand flat so my palm is towards the page because I can point the B to the right. My finger's pointing to the right. And then when I stick my finger out, or I think about my palm, I'm pointing into the page. I could have guessed right away that it was going to be into or out of, since there's already an up and a left right. There's already an up, down, and left right. So I know the third thing is going to be that third dimension. But anyway, it does go into the page. So that would be an X. I'll label that force. I think it says label it somewhere. Is that on the next one? That's on the next one. And then we would say that is into the page. All right, a wire is placed in a magnetic field, very similar to that picture there. Which of the following results will result in a force on the wire? So this is going to get into the idea of the orientation of that wire. So if the wire has current traveling in the same direction as the field, well, that's not going to be at a right angle. And so that is not going to produce a force. The wire has current traveling opposite direction of the field. Once again, that's in the same direction, or not same direction, but same dimension, opposite direction. And so it's not at a right angle, and it's not going to give it a force. The wire has no current. Well, if you don't have any current, you're not going to produce your own magnetic field, and you're not going to interact with the other magnetic field. So that's not it. And then that's got to be the last one, right? The wire has current traveling perpendicular. Well, there's that right angle there, right? Perpendicular, a right angle, and so that is it. If the current is perpendicular to the field, it will receive a force and be pushed. All right. So now we get into the current current carrying wire. The wire is placed in a magnetic field perpendicular to the field so that it gets a force. If the current is doubled and the direction is switched, okay. So more current means more magnetic field. If you want to think about the equation, not B, force, right? Force on the wire is equal to the current times the length of the wire times the strength of the field, ILB. Is that right? I think that's right. Yeah. Yeah, anyway, I'm thinking I was suddenly confusing the other topic there. And so what are we doing? We're doubling the current. So that's going to be 2 times as big. Doubled, and then the direction is switched. So it's going to go the force is going to go the other direction. So it will cause the force to go 2 times as big. So the force will be twice as big. Magnetic force will have the same magnitude. Nope, it's going to be bigger. Double the magnitude. Yep, opposite direction. There it is. Number 2. Number 2. So it's both double the magnitude and opposite the direction. Reversing the current makes it go the opposite direction. Doubling it doubles that. All right. Here's where we're going to draw the different forces. So show the direction of the current traveling. Again, conventional current goes from positive to negative. And so that current, let's make that red. Current I is going to go this way through that wire, I. So there goes the current. Next, it says label it I. So we're going to draw the force. That's going to come a little bit later. I'll do that. I guess we'll calculate the magnitude of the current. The current, V equals IR. So I equals 13 divided by 6.5 ohms. And that tells me 2 amps of current flowing through it. All right, draw an arrow to show the force. So I'm going to do that in blue. The force, again, I got my hand up, thumb, finger, middle finger. I'm going to go thumb up. I'm going to turn. I'm going to point into the paper because that's what those X's are telling me. And I stick out my finger or look at my palm, and I can see my finger pointing, my middle finger pointing to the left there. So I will draw an arrow to the left. That's a force to the left there. And we labeled it FM. And calculate the magnitude. Well, force is equal to I times L times B. So that's just going to be 2 amps times a length of 0.4 meters. That's 0.8 times 0.5, 0.5 Teslas. And so that equals 0.4 newtons. 0.4 newtons. And then lastly, calculate the acceleration. Again, there's no calculations. We kind of mentioned that, but we'll do it anyway for the review guide. Acceleration, right? Acceleration is F over m. This is Newton's second law from F equals ma. If I know the force and the mass, I can figure out the acceleration. And so the force 0.4 divided by a mass of 200 grams, but that needs to be in kilograms. So it's 0.200. 200 becomes 0.2. And that would be like multiplying it times 5, which gives me 2, I believe, 2 meters per second squared. I'm not going to grab something and check that. I'm pretty sure it's right. Right. And that is a wire placed into a field. And question number 5.